podcast, we're going to talk about Gibbs free energy. All right, so we've already established that reactions with a negative delta H or a exothermic reaction and a positive delta S, or one that increases in entropy, is thermodynamically favored. Got tongue twisted. All right, so this indicates to us that up to this point, only exothermic reactions can occur that involve an increase in entropy. But we know that ammonium nitrate does dissolve in water, and this is an endothermic process, so a positive delta H. And we also know that liquid water can freeze, even though this is going to involve a decrease in entropy because we're going to get more ordered. So Gibbs free energy helps us to understand what drives these chemical processes that are violating these two rules up here of a positive S and a negative H, okay? So it's the bridge between what we can explain. Gibbs can be used to determine what drives a particular chemical reaction. Does it occur because of enthalpy? Does it occur because of the entropy? So basically, Gibbs is going to provide us a relationship between enthalpy, entropy, and a favored process. All right, so here is the equation for delta G. So delta G is equal to delta H minus T delta S, okay, where T is the temperature in Kelvin. If the delta G is negative, then the process is going to be favored. So now you can evaluate these little odd cases where sometimes certain things will happen. So when we start evaluating the signs of delta S and delta H, we can start to get more of an idea of what's driving the reaction and if it's going to be favored or not. We know that a positive S and a negative H is always going to be thermodynamically favored. But if you have, let's talk about the easiest case first. The exact opposite of a positive S and a negative H would be a negative S and a positive H, okay? This is not ever going to be favored, okay, at any temperature, but if you reverse the reaction, then you would reverse the signs of your delta S and delta H, and then you would be favored at all temperatures, okay? Now, the cases where you have the same sign for delta S and delta H, for positive, positive, and negative, negative, can happen sometimes. It depends on the temperature. So if you have a positive S and a positive H, it's only going to be favorable at high temperatures, and it's going to be driven by your entropy. Okay, so at high temperatures, you're going to have a positive here and a positive there. You need a negative, so you got positive minus a positive. So you need for the temperature to be kind of high so that this delta S value that's going to be minus here will be larger than that positive delta H value. So this is an entropy-driven reaction. All right. Now, when you have a negative and a negative, then we have a negative times a negative there, so you really end up with a negative and a positive. So now, if you have a very large temperature, your positive value will get too big and it'll override that negative one. So you want to keep the temperatures low so that positive T delta S value stays small and the negative enthalpy can override and make the overall delta G negative so that it's favorable, okay? So this case, you have an enthalpy-driven reaction, okay, because that negative enthalpy is going to drive the reaction. All right, so let's just start looking at a few examples. So here we have some equations, and we're given Gibbs values for those reactions, and we're asked to determine the free energy change of this reaction, okay? Now, Gibbs allows us to calculate the same way that we did with delta H, where we can combine these equations, flip signs, multiply, do whatever we got to do to be able to manipulate these to make this back, okay? So we can apply these same principles here. So we're going to go ahead and start making it. So we're going to start with the B2H6, and I see that in the second equation here. It's already in the reactants, so I can just go ahead and write it as is. Okay, So I'm just going to go ahead and write this equation down. And then after I do that, I'm going to also add the value out here. Okay, I didn't change anything, so no need to change anything about my value. Okay, so I got these made. All right, now Cl2. Usually we would skip a diatomic, but you really want to look and see what things are occurring in different equations. Okay, H3BO3 occurs in two different equations. Okay, but it's not anything we're trying to make, so it's really not an issue. Cl2 is only going to occur in one of equations, so we're probably going to have to try to make these. Now HCl, you see, is also made in two equations, and we want it in the end. So this is like an O2 in a combustion equation. It should work out in the end because it is in multiple equations, okay? So we're going to worry about this Cl2 now. Cl2 is going to be from this equation. It's the only equation that has Cl2. And it's already on the reactant side, so there's no need to change the direction of it. You can just go ahead and write the equation down. And we're going to write the value as well. Okay, so we got negative 92.3. Okay, now understand that we need to make 6 Cl2. So I'm going to have to multiply this whole equation by 12. Okay, so we got 12 and 12. Okay, and that means I also have to multiply my delta G value by 12. Okay, so that dealt with those. All right, now we're going to worry about the BCl3s, okay? There's only one equation that has those. It's the first one. They are not in the right spot, though, so we are going to have to inverse the equation. So we're going to write this side first, so the product side first, and then we'll write the reactants, okay? All right, and I'm going to go ahead and include my value. Because I reversed my equation, I'm going to write a positive value instead of a negative value. I'm going to reverse the sign. Okay, now if you look up here, I should have 2 BCl3s, and I think I'm only given 1 from the equation, so I need to multiply the whole equation by 2. So we got 6, we got 2, we got 6, and then we got 2. And then, of course, this value also has to be multiplied by 2. Okay, so that should have got us, because we're going to hope that HCl works out since it occurs in several different places in several different of these equations. So if not, we're going to have to go back to the beginning and start all over, right? We'll hope that doesn't happen, though. All right, so let's start canceling things that are alike on both sides. We have a 6H2O and a 6H2O. Okay, and then we have 12 divided by 2 is 6 H2s and 6 H2s. We have 2 H3BO3s and 2 H3BO3s. And we have 6 HCl's and 12. So cross out the 12, that leaves us with 6. Now let's try adding it up and see if it gives us back the original equation. Okay, so we got B2H6 and 6 Cl2s on this side. And that's going to give us 6 HCl's and 2 BCl3s. Look at your original equation and you'll see that it matches perfectly. All right, now what you want to do is get the value for that. So you're going to have to add all these values up. Okay, so when I add all those values up, I get negative 1376, and that is in kilojoules. Okay? Now, is this reaction favored? Well, delta G is negative, which indicates to us that this reaction is favored. Okay? If so, what drives the reaction? Okay? Well, that's going to be sort of difficult to tell based on the data we have, but we can attempt to try to gain some insight. We really don't know anything about delta H. Okay? But we can determine a little about delta S just by looking at it. Okay? All right, so we do have all gases, and then we have 7 moles on this side and 8 on this side. So we are having an increase in the number of moles, so we're likely going to have a positive entropy, which means that this reaction could be driven by entropy. If it is endothermic, meaning a positive H. If it's exothermic, then it is driven by both the enthalpy and the entropy. So really, we'd have to get a little more information. Okay? All right, let's look at a different example problem. All right, in this one, it tells us that that's the equation for the combustion of phenol, and it tells us that the delta H of combustion for the phenol is negative 3,058 kilojoules, okay? And then it wants us to determine the delta H of formation of phenol, okay? And we're given this chart. So we're going to have to do some products minus reactants, okay? So we have 3 H2Os. So we're going to have to do 3 times negative 285.85, okay? And 6 CO2, so 6 times negative 393.5. All right, we're going to add all those up because those are all of our products. And we're going to subtract the reactants. All right, you see that the O2 value for formation is 0, so I don't have to worry about O here. And the phenol is what we don't know. And that's equal to that total that was given to us in the beginning. Okay, so now you're just going to start doing some canceling and getting the correct answer. So if I'm plugging in my math, I'm getting this so far. Okay, and then I'm going to go ahead and combine these so I can get all those worked out. And I get this. And then I need to combine like terms, and I get 160.55 is equal to negative x, and then I bring my negative sign over to make my x positive, and I see that I have negative 160.55 kilojoules per mole. Okay, and that is the delta H for the phenol, right, formation. Okay, all right. The second part of the equation asks us to calculate the free energy change. Well, to know the free energy change, we would have to know the delta S. So again, we're going to have to do some products minus reactants. Okay, so we had 3 H2O, so we're going to do 3 times 69.91. And we had 6 CO2. I have to scroll up a little to get that value. Okay, we got 213.6. All right, now remember that in entropy, O's and diatomic elements do count, right? Okay, so we had 7 O2s, so that's 7 times 205, and then we had 1 phenol, so 144. Okay, and that should give us our delta S once we get all this worked out. Okay, all right, so just getting our math simplified a little bit here. I'm getting this on my product side. And my reactants, I am getting this. Okay, and then I'm just going to start combining. All right, and that gives me negative 87.67, and this is your delta S, which is in joules, right? All right, now we got to get to delta G. Okay, so we're going to do a little delta G equals delta H minus T delta S. Now, entropy is in joules, and the enthalpy is in kilojoules, okay? So you can convert either one you want. I'll just go ahead and convert with this one since it's down here. Okay, so I would have negative 0.08767 would be kilojoules for my entropy, okay? So now I'm going to plug in my values. Delta H, I had negative 160.5. Oops. Look at that, y'all. And y'all aren't even here to tell me that I'm screwing up. All right, so that is just for phenol, right? So really that's kind of a trick question. So the enthalpy of the combustion was this. It was given to us in the problem. Our temperature was 25 Celsius, so add 273 and you'll get 298 Kelvin. And then you need to plug in the delta S that you just found. Okay, all right, so now we're going to get this math simplified a little bit. All right, and when we get the math simplified down, we see that this side is 26.12, and you have a negative, which makes a positive. And then you work in that negative 3,000, and you get this in kilojoules. Okay, so this is your delta G. Okay, so this means that this reaction is favored because it has a negative delta G. The other thing that could have helped you out was that it had a